Right. Hi everybody, my name is Brandon Shrewsbury. I'm the CEO of Boardwalk Robotics. If you guys are not familiar with Boardwalk, we are a spin-off of IHMC. The goal is to commercialize an audio one day. We still got a while, but in between then and now we offer commercial services. We're basically trying to help you use the tools that we have developed to create this robot. And we like to do weird stuff too. So if anyone wants to make a Stegosaurus or you're interested in making robots for Legoland, we would love to be a part of that. We offer just about everything that all of the other commercial people trying to do humanoids do. The big thing that's different is we'd love to come help you build your robot. So if you, like I said, are building something, if you're stuck on a problem, if you need help making a visualizer, if you're having a hard time recording data, we have done this already. And actually most of the software is open source, so we would help you integrate it and then hand it off to you so that you don't have to pay a licensing fee. And if you ever need extra features, we're there to help. This is the visualizer that we use. It's called Simulation Construction Set. It was made by that man right there, Simulation Construction Set 2. Here we've got a robot log of pushing Nadia during push recovery, and there are, I think, 15,000 variables. We record like 2,000 or 3,000 variables at kilohertz, and another, whatever's left at like 333 hertz. And there's tons of features in here that make actually tuning your robot much easier. This is not only a visualizer, it's also our simulator. It's in the back end and the logger. So it's one interface that does everything. All right, so now on to Nadia. The question we get all the time is why hydraulics? The answer I usually give is why not. The hydraulic pump off board provides both energy and a way to cool the fluid. So if you were to try to make electronics energy dense, you typically have a heat problem. We solve the heat problem by just having a giant pump on the board. There are a lot of disadvantages, but we are not in a situation where they matter much, which is nice. We've been working on Nadia since 2018. Some work happened before this. Now we're at a full humanoid robot, and we still have a long way to go, but it's been pretty fun. We use the Haloti motors, I'm not sure where Jesper is, for our hip yaws, and it didn't end up working too well for us because we put a cross roller on the output and killed the quasi-direct driveness. In theory it works excellent, but whenever we load the leg, we had a really strong loading condition for the bearings that we chose. They're kind of friction. Most of the actuators besides those are ISAs. These are called Integrated Smart Actuators from Moog. They seem awesome. They're 3D printed titanium. They come with a linear encoder, EtherCAT, load cell. They're the dream. Moog quickly discontinued them. There were not enough people to adopt the actuator, and they said, good luck. Here you can see our hip joint. It is a dual 4-bar. This is force control. They say you're not supposed to get near hydraulics. Obviously, we don't listen to that very often. We get about 240 newton meters peak and 12 radians per second, which is excellent for us. One of the things that was very difficult is the ISA only comes in one size. It only has 100 millimeters stroke. So we did some design optimization to try to figure out how to maximize the joint range of motion, torques, and everything with that stroke. We did finite difference in sim, and then just played with the link lengths to look at the lever arm that got out to try not to get near a singularity. This was awesome in practice, but then backlash came in and it kicked our ass. You can see we get around 114 degrees pitch and 80 roll. It's not a perfect square, of course, since it's a differential. And it is a very, very tight packaging. As Josh mentioned, the thigh is the structure. So we have all of the actuators just hang off this thing. Then we put the thigh on and mount it to the bottom. It's very difficult, and the packaging is very tight, and the actuators have a swept volume because they move. So getting that thigh very, very tightly packed in there was a couple of years. You should not do it in a couple of years. You should just do a less optimal design. Our knee is an inverted 4-bar. So here you can see where we broke the actuator. Right there it's broken. A little ISA thing pops out, like the little alien from Aliens. The thing that we messed up here is the 4-bar lever arm gets smaller as the knee collapses, so we get weaker as we go down. We were really hoping to be able to do one-legged knee bends, but we'll have to do some work when we redesign this. It also ruins sim. We would much rather have serial joints. The ankle has 900 newton meters available to it, and that's because the ISAs only come in one size. So after you do all of that, we get Nadia running. Like I said, we're cheating because a pump was off board. We're working very hard to get it on board, but I try not to show any of the super cool videos because a few of my colleagues will try to show them. This is a GPU planar region detection, so it has like a a real sense. It gets the depth data, throws on the GPU, pulls out some areas that it thinks it can walk in. I think it's using like A-star or something to figure it out. The top right is fast walking, and Stefan will be discussing that soon. It's just a different type of walking controller. This one that finished too late was an angular momentum, trying to use the arms to cancel out the angular momentum. Our legs are super heavy. So every time you take a step or a swing, all the inertia is down to foot, or most of it is down there, and it causes a lot of problems walking fast. And then of course, Savan here doing some VR. We had a lot of fun with this project. Most of the time though, we spent here in boring land. So this is two ISAs pushing against each other, and we tried to figure out all of the firmware problems, how to solve all of the dynamics of the actuator. We thought we were buying a complete product, and it turns out Moog doesn't do force control. So they made an excellent actuator for aerospace and screwed us a little. It was great because we didn't have to do any of the mechanical part, which we would have sucked at the time because we didn't know much about the internals of hydraulics. But we way overestimated or underestimated how much effort it was going to take. The hydraulic valve in the top right-hand corner sort of shows you how a differential or a proportional valve works in hydraulic land. The red is a desired set point for the spool, which is that bottom little lance that moves back and forth, and the blue one is what the ISA can do. It's about 4% per millisecond, which is a 4% slew rate. That means that when you have a desired spool or force, that thing has to move to let fluid in. Fluid that goes through is directly proportional to velocity, and then we use that basically flow shoving in to create force. And this means not so great force control. Because of that slew rate limit, we get this thing called pilot-induced oscillation. So you have a desired force that goes down, let's say the red here in the top corner is your desired force, nice sine wave. The light blue, the yellow is that measured spool, and by the time you finally get to your desired is going the opposite direction. And in reality, you're going to have delay, you're going to have physical, comms, any kind of delay that you can think of. So if you use a lead lag filter with a rate limit, you can turn that garbage into that blue line, which still sucks, but at least it's going the right way. And here's I know there's not an ISA that you can look at, but on the top is a desired position in impedance control. So you're moving the actuator with some square wave, and you get this terrible ringing. And this is with PIO off, and then you turn it on, and everything is fixed. And here you can see the desired, I believe this one is the desired spool. And then eventually the desired spool stops being so nasty and starts going back the right way here. So shoots back, hits here, like, oh God, I'm going the wrong direction. Here it's like, oh, you're going the opposite direction. Let me try to fix myself. So force control on the ISAs, 30 hertz is kind of the gold standard. We tried 40 and we hit that rate limit. So we're like, okay, we're absolutely limited. We'll never be able to do better than 40 without changing the spool. And even with PIO on, it doesn't freak out, but it does have this pretty serious phase shift. One other thing that's kind of interesting about hydraulic actuators is that because it's a flow, hydraulics is a flow source, or our valve is a flow source and not a force source. So we have to figure out a way to relate the amount of flow based on the spool position. And this is just a magic lookup table. If I could describe Nadia, it would be adaptive lookup tables. So there's two things sort of being captured here. One is that spool lance, as it moves, it's got several cuts in it. And depending on where it is, it changes the flow. And this weird shape is trying to capture those notches. And then that 0 point, it never is actually 0 because the null position changes with fluid viscosity and the temperature of the actuator and whether or not the encoder is aligned properly. There's no ground truth here because we don't have a real way to measure it. It's just a measured property of the actuator. And with lots and lots of work, we were able to hit 27.5 hertz force control. This is on one side, we're doing 1,000 Newton amplitude at 3,000 offset, which means we're not going through backlash. I'm sorry that the text is so small, you have to use binoculars. We also had temperature problems. The load cells supposedly are wafer-based. I know, I don't want to know any of this. And they said basically, they put everything together. They never really cared about zero force control or trying to get very accurate force control. They just put it on there and thought it would be nice. The load cell drifts about 250 newtons depending on the temperature. This whole actuator is an oven. It generates heat. So we said, please, can we do something? Yeah, come up with what you want to do. So we just glued load cells or temperature sensors all over the load cell and the actuator on the outside to find out where we wanted to put a temp sensor. And they said, sure, just give us a lot of money and we'll glue one on the inside. So we sent all our actuators back, they glued them in, and we built a lookup table. Yes! What we learned on Nadia, we learned how to do a lot of things wrong. So we tried to get a custom force torque sensor. That ended very badly. We tried to go without hip encoders. That was the backlash thing I was talking about. Backlash sucks, hydraulics are hard, electric actuators are hard, everything is hard. We got stuck in a lot of rabbit holes. Things seemed really important that were not important at all, and things that we thought were going to be really easy and take 10 minutes are not finished yet, and we started at the beginning. What went really well? We got an awesome robot face. In the end, the Moog ISAs were a good call. We would not be where we are without them. And I don't know anyone who's ever got an actuator and been like, yes, this is great, nothing is wrong. The joint torque, the output, and the joint speeds right now are excellent. Until he started working on running 2 months ago. So we actually are doing force control. And this opened up a lot of new problems. We use the old DRC Atlas at IHMC. And I don't really know how it works because it doesn't have hip encoders, it doesn't have load cells. We just use the pressure on the inside and it's a black box. It magically works, and we have no idea how, and we've had the thing for 8 years now. Yeah. Our leg structure is awesome, but it's really, really difficult. We spent, I think, 2.5 years trying to get that thigh shell as beautiful as it is. And as nice as it looks, the amount of effort it takes to fix anything is ridiculous. But you do get crazy 3D structures. You could just 3D print titanium like Lost Dynamics, maybe that solves the problem. We have great uptime except for the arms. A couple of people have wanted to throw the robot into the lake next to IHMC when the arms break. And they break because we're using T-motors and we don't know how to get them to work, which is idiotic. We have contacted the manufacturer and they said, oh, the boards we got manufactured were wrong. We can't send you new firmware because we changed the STM chip. We're just going to send you new boards, and they were used for the wrong kind. And we just gave up. So we're making this. The arm is based on an open loop cycloid. We are very proud of this, but it's also ridiculously hard and took way longer than we wanted. It's a 22-to-1 quasi-direct drive. I don't have the rotor in here so you can feel just the transmission. And I'm not going to talk about transmissions and back drivability. So in the top right hand corner is our HPU. We want to put that on board. It's one of those things that it's a trial and error problem. We don't understand the cooling yet, but we're pretty excited. And because we can't use the ISAs anymore, I didn't have a cool picture of the assembled one, but we definitely have some of these assembled. And we're waiting on electronics like everyone else. And this is the 3 versions of the cycloid we have. Our biggest one is 150 Newton meter output. The other one's 80 and 20. We are hoping to sell these eventually. We are not ready yet, but soon. All right, the part that I really wanted to talk about. So we are interested in doing design optimization. All of the parameters that we're talking about for carbon fiber thickness, we're looking at new hydraulic actuators. We want to use our sim to size everything. And I would love to talk about this with people who are trying to do the same thing. We are interested in everything. We don't know how to do it. We have not really started. We've only been talking to people. And on our side, we've broken it down into 6 steps. We do everything in Onshape. Onshape has a great REST API. We can get meshes, center mass, inertia. We can talk to it, supply it with variables. Everything's through JSON. So we think we should be able to do a really good pipeline. But Josh, as he mentioned recently, you shouldn't try to optimize anything until you've made it once, because you don't know what you're doing. That's very true. The parametric design, we've had a big issue where if you change anything, if you change a length from positive to negative, it will be, no. If you change something from a positive to negative in CAD land, sometimes it flips your plane upside down, and then everything is broken. Java to Onshape, we do everything in Java. Anybody else? Yeah. It's Jesper, he worked at agency. So Java to Onshape, hopefully this part won't be too complicated, but we're kind of trying to rely on Onshape to do our collision checking. You saw the carbon shell, the hydraulic actuators that go in there, the sweat volume is very difficult. So if you were to try to do it in Java, you'd have to decompose everything into smaller topologies, and Onshape already does it. The optimization part is in itself an open question, and we would really like to do hierarchical, where we know a lot about the transmissions. We shouldn't have to do a complete optimization step to try to figure out what should be good. We should be able to just do like gradient descent or small thing to seed the next round. Simulation, hopefully you guys liked these. I love this, but we're trying to shoot as many sims in parallel as possible. Hoping to do a lot of these as open loop so that you're not actually using physics. You just kind of use the inverse dynamics calculation, take your output, feed it back to your input so everything's perfect. And that speeds things up a lot, but it's lying to yourself. And the last thing is, how do the transmissions and everything fit together? This is the team. This is not everybody. We have a lot of people that come visit. Sometimes as quick as like 2 weeks, sometimes as long as 2 years. If you have students or you're interested in coming here, please let us know. We love to take people. We have 2 organizations, both Boardwalk and IHMC. As you see, we're very serious people. We would love to have you. And there once was a German man with a beard whose mischievous nature often appeared. He planned a fun conference, dynamic walking in abundance, offering beard cuts, all cheered and revered. You're clapping for ChatGPT. And Johannes offers really awesome beard trims. For free. Yes.
So cheap.
Yeah.
Do you happen to know like the electrical power draw of Nadia when it's walking, or like if you put the hydraulic pump on board, like do you know like maybe a rough battery life you'd expect?
So you guys remember? You asked me.
It's usually like 2 hours, right?
Yeah, it's 15 minutes. Way off.
What?
Yeah, so the answer is you have a hydraulic power unit and your flow is a fixed displacement motor. If you want 18 liters per minute at the 3000 psi, you don't get your energy for free. Hydraulics aren't very efficient. You have to offset that. Our battery outputs, I think 120 amps continuous. It's ridiculous.
At 120 volts.
At 120 volts. So
It's dangerous.
our pump requires 5.6 kilowatts.
Now that sounds ridiculous, but Atlas's pump is also 5 kilowatt and 5 kilograms, so we're still behind them, but we're trying to catch up. Any more questions? Yes.
Yeah, so now that you've built this robot once, are you trying to scratch it and go, let me phrase that. Would you try and go ahead this route, or would it be better actually to scratch it and start from?
So we have a real difficult problem of being able to just build a new robot. We have the humanoid of Theseus instead of the quadruped. So we would very much like to replace the arms, but to do that we need to make some weird adapted, changes. And we'd like to put the HPU, battery, and the arms on a new torso, but it means that we have to make sacrifices because we can't replace the pelvis yet. And the timing and people don't work so that we can start over. None of the controls engineers want just this. They want incremental upgrades, and it makes everything very hard. Yes?
So what's the reason behind you use cycloidal gears for your arm actuators?
So I spent some time at Haloti, and I like quasi-direct drive, and the person that was here was very excited about cycloidal. And we thought, okay, let's do the same thing. So we spent a ton of effort, and then we found a paper out of Korea that already did it, and we're like, oh, well, at least that means we're not wasting our time. But really hoping that we don't like harmonic drives. We don't like the inertia. The goal should be to have the largest transmission you can that's transparent. And the reason we want the transparent gearbox is because we hit everything really aggressively, and we're tired of breaking the robot. And I don't know if there's another reason outside of robustness, but we break everything we put on the robot.
Can you put slip clutches?
So that is definitely an option, but it's additionally, so we would need a torque cell, and we would need a clutch, and it would need to be more complex. And this does have like 200 bearings in it, but I'd argue it's less complex than the transmission. Any other questions?
Which size is this?
This is the medium. This is
80 Newton meters.
80 Newton meters output. It's not perfect. No actuator is. It's fairly light, but with cycloidals, it's very weird because the input shaft feels the feels the cycloidal discs, and if they're not manufactured perfectly, it causes a lot of problems. And the backlash is inconsistent depending on which position you're in. We've ordered like 50 disc sets, maybe, to try to reduce the backlash. We got it fairly good, and then ordered them again, and they were bad. So it turns out we weren't good at making drawings. We were just lucky.
Can I ask a question about your torque and velocity and stuff like that?
Yes.
Okay, so you're starting out with a pump, which is a displacement pump. And you're not using traditional move valves, which are velocity valves, or you are?
We are using a special valve. They took the E24 valve and separated it in half for no reason, so that they could prove that you could control the spool lengths by wire. So it's got a weird PD controller on it. Their traditional valves have like 20 times the bandwidth that this does.
They've got like kilohertz or something like that.
I don't know the exact number.
So but your valve has a pressure output instead of a velocity output?
No, it's velocity output.
So how do you say that you got torque control?
We get it, but we're banging the valve back and forth.
And why is that different than using an electric motor with a big reduction?
It is not different. The reason we're doing hydraulics is because we are taking advantage of the cooling that we get for free by the...
So what did you say about transparency?
Oh, that was for this guy. If we have wondered a lot whether or not we could put something squishy inside the actuator, in the hydraulic actuator, so that it's not so bang, so it's not so ridiculous.
And then it's got a series last.
Yes, sir.
But, which doesn't work well for people nowadays.
Yeah, I think that it's probably very beneficial, especially in this case. I don't know if anyone's ever tried it. We don't know exactly what Atlas is doing. I don't think it's that, and they still seem to get great performance. I guess you could question whether or not they get good force control. Maybe they don't need good force control to be awesome.
Do you know if they're using force control?
We have talked to people who've worked there in the past, and they say they're pretty much doing the same thing as us, but they could just be lying to us.
You are doing force control
Yes.
through feedback with your velocity actuator.
Yes, sir. Yep.
And it's at what? And that's the 30 hertz, 40 hertz you're talking about.
And that the closed loop is around the load cell, which is awful. I think all load cells are awful. Has anyone developed a better load cell?
You say the load cell's slow?
No, it's awful. We're so tired of reading noisy data from strain gauges that suck. If someone here is a material scientist, please devote your life to fixing that for me.
The load cells, why are load cells a problem?
So our load cells is exacerbated by the fact that hydraulics are so stiff. So I'm blaming it on the load cell, but it's really because we picked
The
the
load cells
job.
are choose the elastic material,
Exactly.
the load cells perform pretty well, I think.
We have a problem with them being noisy and then drifting with temperature. And I think those are the two things that we have not been able to perfect with our adaptive lookup table. We should probably do something slightly more complicated. There was another question? Yes.
I was just going to say, thanks for a really great talk behind the hood, if you will, under the hood of this, and I want to give you a little tribute in Limerick
Whoa!
for yours. Learn some lessons from building the Nadias. Any motors present lots of gaudiness. Lots of time spent to actuate, lots of tables to compensate, torque and backlash, and limiting how hot she is.
So if you haven't been to dynamic walking in the past, limericks are usually pretty key. Please add them to your presentations if you can. I feel like also, if you want to keep the beard tradition alive. Thank you.